Alrighty, so we're going to start talking about the area known as equilibrium reactions. Okay, equilibrium reactions. As it turns out, we can kind of think of reactions as having a forward direction. Whoops, try that again. A forward direction and a back direction. If you notice, uh, these are supposed to be superscripted. I'll have to fix that. Just realize that. Anyway, I'm going to keep it this way in the video, but I'll fix it in your notes. That being said, there's a forward direction, and you can flip it around so that the products themselves can go into the become reactants, and the reactants can become products. So there's a back reaction, and in principle, all chemical reactions have some degree of reversibility, where there is some degree of back reaction. That being said, it's not, in some cases, it's a really small amount that goes in the back reaction. And in fact, for all practical points, when it goes, when it has a super duper small back reaction compared to the forward direction, we usually just treat it as a one-way reaction, that it just goes in one direction. But in reality, to some degree, it may be hard to measure, but in principle, there's a back reaction to every chemical reaction. But there are some chemical reactions where the back reaction becomes a little more substantial, something that definitely can be measured easily with modern techniques, even not even that modern technique. And when we get a situation like that, we actually have something known as an equilibrium reaction, and we write it this way. We write we write the reactants on the left and the products on the right, and then we have this two-way arrow. And whenever you see a two-way arrow like that, it really means that the reaction in the back direction is actually significant and needs to be considered when studying this reaction. So whenever you see a series of reactions that have these two-way arrows, that is indeed what we're looking at. Now, uh, that doesn't mean that the back reaction goes to this same extent as the forward reaction and vice versa. Sometimes these reactions can reach a point known as equilibrium, and I'll describe that later. When they reach equilibrium, what you'll find is there may be more products or more reactants on one side than the other. So they don't necessarily equalize in terms of concentrations. And we'll deal with that in a short bit here. So the beginning to all this is understanding that there are types of chemical reactions that actually have appreciable back reaction, and we need to account for it. So when you're thinking about it, then when you're looking at this and you see an arrow like this, you think, aha, here's my reactants, here's my products. Reactants can go to products. But sometimes the products themselves can be reactants, and these reactants can become products, and it can go back that way. So you're going to kind of see that they can go either direction, okay? And we have seen this before, believe it or not, and I'm going to remind you of something that we looked at. Remember vapor pressure and dynamic equilibrium? We covered this when we went, like one of the first things we covered in our class in the first couple of weeks of this class. And so let me just remind you of what this is all about again. So let me use my very poor drawing skills, but I'm going to try it. Here's a beaker, okay? That little shakiness is from my coffee this morning. And let's say we have a cover on it. So we have a cover on this beaker, okay? And then we have some liquid. We'll call it, well, we'll say liquid water. Okay? Well, if we know we cover this up, you remember that some of the liquid particles, the water molecules, are going to have enough kinetic energy so that they can break away from the intermolecular forces of attraction that hold them together, and you will start to see the you know, a point where there's going to be gaseous water above the liquid, and we call that vapor pressure. Well, one of the things that can happen is eventually enough water will develop in the gas phase that you'll reach a point where the water will also start, the gas water will start smacking back into the surface of the liquid and rejoining the liquid phase at the point where the rate of condensation equals the rate of evaporation. That means we're at, we called it a dynamic equilibrium. Okay, so the rate in the condensation, that's the gas going back to liquid, equals the rate of evaporation. So what happens is there'll be a constant concentration of water in the vapor phase. So the concentration of gas water is not changing. And so when you reach this dynamic equilibrium, it just means that the reverse reaction and the forward reaction are equal in terms of their rates. And so that's what we taught you early on in this class. And really, we can apply this same concept then to an equilibrium reaction. So I'm going to do that. You may be hearing some noises in the background, and that's because I'm in my backyard making this movie right now. And my new puppy, well, I say new, he's about 4 months old, is running around investigating. And right now, apparently, he is fighting a big stick. So you might hear that stick going, just so you know what the background noise is. You might hear him growl too, because he gets pretty serious about this thing. Look at that. Just crazy. Okay, back to my video. Hopefully you enjoyed that small puppy break. And I need to just get rid of this. Okay, now as I was just saying before I got interrupted by my puppy, we will continue on. So looking at what I just showed you, that the rate of condensation is equal to the rate of evaporation when dynamic equilibrium is formed with vapor pressure, we can go ahead and take a look here. We can apply that same principle to a chemical reaction. So we can think of this direction going from left to right. We'll call that, for the purposes of this discussion, the forward reaction. And I bet you can guess what I'm going to call the back reaction. I'm going to call it the reverse reaction. Okay? So when we reach equilibrium, so if you start off, think about it, what happens is you'll start off with all reactants and no products before the reaction takes place. Then the reaction takes place and you start losing some reactant and gaining some product. That's forward reaction, moving in that direction. Eventually, though, you'll start building up enough of this product so that it can become a reactant for the back reaction, and the rate starts to increase over time. And it speeds up and speeds up and speeds up and speeds up until you reach equilibrium. And when equilibrium is reached, the rate of the forward direction is going to equal the rate of the back reaction, or the reverse reaction. And quite frankly, that is the point where we reach equilibrium. So unless this condition is satisfied, you will not have reached equilibrium. So that's the key take-home message here. Equilibrium's reached when the rate in the forward direction equals the rate in the back direction. And that's when we say equilibrium's formed. And when that happens, the concentrations, so at equilibrium, okay, the concentrations of the reactants, okay, and reactant and product concentrations are constant. They don't change. They're not equal necessarily, but they are constant, meaning that they're not going to change anymore when equilibrium is reached. And it's a lot like what we just said above here, using this as our point of overlap from past material. You can see the same deals going on here. Just like I said, the concentrations of gas doesn't change and liquid doesn't change. The concentrations of products and reactants are constant as well. So let's continue on with that thinking, and I'm just going to use a really simple equilibrium reaction just to help you out here. We got A goes to B, so that's my simple little reaction. And I'm going to write above this that there is a rate constant for the forward reaction, and there is a rate constant for the reverse reaction. Okay? That's how it goes. And so we can then say at equilibrium, we know that the rate in the forward direction equals the rate in the reverse direction. We've been saying this all along. Whoops, that's rate in the reverse direction. All right? So let's say, for this case, we'll say that we're first order with respect to A. So we can replace the rate of the forward direction with it. So let me go back up here. So the rate in the forward direction, let's say the rate law is Kf times concentration of A, and we'll just say it's first order. And then we can do the same thing for the other one. So the rate in the reverse direction, we'll call that Kr, and that is equal to the Kr times the B, concentration to the first power. So we'll just assume that it's to the first power. Okay? So what that means then is we will be able to replace rate of the forward direction with the rate law and rate of the reverse direction with its rate law. So and then set them equal to each other, because that's what happens at equilibrium. So instead of saying rate of the forward direction, I'm going to say Kf is equal to concentration of A, and that's we can set that equal to Kr times the concentration of B. All right, and so one thing we can do then is we can isolate the rate constants on one side. So I'll just divide both sides by Kr. And I'll divide both sides by concentration of A. So what you get from this then is a ratio of rate constants is equal to a ratio of concentrations. Well, at a given temperature, we know that these rate constants are not changing, so they're constant. So when you take one constant and divide it by another constant, the resulting ratio is also a constant. And so this is going to be equal to, and I'm just going to say a constant unchanging ratio. So this ratio does not change. So you have Kf divided by Kr is equal to concentration of B divided by concentration of A. And remember, this is all once this reaction hit equilibrium. So what we learned from this is that at an equilibrium, a given equilibrium, the ratio of the products divided by the reactants is fixed. It's constant. It doesn't change. It must be maintained, just like the ratio of rate constants is constant and must be maintained because you have a ratio of constants. Nothing's going to change. So at equilibrium, once you know the equilibrium, you know the ratio of products divided by the reactants. And we call this whole thing an equilibrium constant, K, capital K. And when we define things in terms of concentration, that's known as a Kc. So that's what we get, a Kc there. So, so that's an important thing to keep in mind, this thing called a Kc. There's other types of equilibrium constants, and I'll talk about those later. But the Kc is the ratio of concentrations, okay, at equilibrium. And these are just not any old concentrations. These are once equilibrium is found. So we'll call those equilibrium concentrations. Before they're at equilibrium, they can change, and the ratio will not be the same. The ratio is only gonna be constant when we take the concentrations at equilibrium. So let's apply this a little further to a more complicated system. Except before I do that, I want you to also see that you can express an equilibrium constant a lot of times using a ratio of rate constants. And I feel like I need to apologize to you because we're going to use the letter K a lot. We're going to have equilibrium constants called Ks. We have rate constant called Ks. Little rate constants, lowercase rate Ks, are rate constants. Capital letter K is an equilibrium constant. And so that's one thing you need to keep straight. But for some reason, and maybe it's because of a lot of the heritage of chemistry, a lot of this stuff was worked out in Germany. In the Germans used K a lot for constant because they spelled constant K with a K, not a C. And so we see a lot of Ks. And you've seen other ones too. There's not much we can do about that. So the K is used a lot. And it's going to continue to be used a lot. All right. So let's move on and apply this more generically, this whole idea that you can express the equilibrium constant, which is by taking the product concentrations for a reaction and dividing them by the reactant concentrations. And then we'll take a closer look at that. So looking at equilibrium constants, we can come up with sort of a generic way of expressing them. So I'll just use another quick example here that I'll just make up. And again, I'm not going to use actual chemicals for this part. I'm just going to use some representative things, and you'll see what I mean. So let's say I had 2 molecules of A that react with 2 molecules of B, and let's say they form 3 molecules of C. So that's kind of what an equilibrium, and it's equilibrium, so let me change the arrow. So it's not a one-way arrow anymore, it's a 2-way arrow, like that. All right, so based on what I told you before, we need to take, if we want to calculate the K, and I'll call it the Kc for concentration, we can take the concentrations. So another way to look at this top one here is that I have A plus plus B plus B, because there's two A's and two B's, so I'm just kind of writing it out longhand, and then three C's. That's what this means, right? When we say 3C, there's three C's. Two B's, there's two B's. Okay? And so what I can do is then write out the concentration. So we need, and here's the interesting part. When we look at this, in order, and again, it's just part of, it's beyond the, I'll say it's beyond the scope of this particular class, but the fact is when we see three C's, instead of adding them in the equilibrium constant, we multiply them. So I take the concentration of C times the concentration of C times the concentration of C, because there's three C's. So I got to multiply all of the products that show up. Let's add one more layer here. Let's say we also had a D there. You see that? So then this would be D. So what would I do? I would multiply the concentration of D there as well. So that would be how we dealt with those. We just multiply everything that is added together for products, and then we do the same kind of thing for A. I take the concentration of A times the concentration of A times the concentration of B times the concentration of B. For each one of these, we multiply them out. Now, maybe you're realizing something at this point. Wouldn't it have been easier just simply to say, since we're cubing C, just say concentration of C cubed times concentration of D? And then we could, because we're squaring essentially the concentration of A times A, B times B, we're also squaring B. We can do this like that. So we can have A squared and B squared. All right? So that's how we do this. So, excuse me. So we can write out our equilibrium constant as then C cubed times D times A squared times B squared. And what's kind of interesting to note, all we did was take our C and raise it to the stoichiometric coefficient. And the reason why is because of what I just showed you. And we take D, there's only one D, so it's just D. We have two A's, so we took A and raised it to the stoichiometric coefficient. And we had two B's and we raised that to the stoichiometric coefficient. So we can write a more generic way of doing the equilibrium constant. We can simply just say, if I say little a is my stoichiometric coefficient for big A, which is my reactant, plus the stoichiometric coefficient little b times B for my reaction. So I have my two reactants, and then I have my equilibrium arrows, and then I have a little c and a big C. Those are my products. C is just representing the stoichiometric coefficient, and then I have a little d and a big D. I can now say that if I want to know my equilibrium concentration, and my equilibrium constant, I should say, in terms of concentration, that's what the C refers to, then I have to just follow this generic formula. I take my products raised to the C power plus my other product raised to its stoichiometric coefficient. I said times, and I saw this here, and I just these are multiplied. Don't put a plus sign there. You know, that's a really common error that people do. They'll put a plus sign instead of multiplying. So these are multiplied, and then you can do the same down here. A raised to the stoichiometric coefficient times b raised to the little b power. So just make sure you do this, and you can apply this anytime you see an equilibrium concentration. Now, there are a few rules about this that I'll teach you in a workshop. You'll learn as you go about how to express equilibrium constants, and so we'll look at those in a workshop that you're going to see soon enough. Okay? Well, that is the end of this video.